So today we are happy to welcome Joshua Ruiter from Michigan State University. He's going to talk about abstract homomorphisms of some special unitary groups. So please.
Great, thank you. Yeah, it's great to be here. It's supposed to be 50 minutes with 10 minutes for questions at the end, or 60 minutes, just to clarify.
60 minutes if you want. Okay,
okay, great, thanks. Yeah. Yeah, thanks to the organizers for having me. All right, let's start. Let's not dwell too much here. All right, so let's fix field K. And we're going to talk a little bit about a comparison with Lie groups, because that motivates some of the sort of the central conjecture here. So we have a forgetful functor from Lie groups to topological groups, which I'm calling U here. You just take your smooth manifold and you forget that it's smooth, and you forget that your morphisms are smooth, and you just think of them as topological group maps, so just continuous things. And then this functor S is not really forgetful, but it's sort of, I don't know, a little bit like a forgetful functor in some ways, but it's not really. From affine algebraic groups to groups where you just take the group of K points over your field. And there's some nice parallels between these two functors. And it motivates a lot of what I'm going to say. So one of the things that is really interesting about, or sort of the underlying philosophy of this abstract homomorphisms business, is that a lot of the times you just get more than you ask for in terms of the morphisms. So the sort of big example here is a theorem of Cartan, which says you can phrase it in terms of this forgetful functor. But the original formulation just says you have a continuous group homomorphism between some Lie groups, then it's also smooth. So in other words, this forgetful functor is full. It takes every just morphism of topological groups between Lie groups really arises from a morphism in the Lie category. And yeah, this is saying somehow smoothness, which is much stronger than continuity, you get for free without asking for it in a certain context. So the question to ask is, what about this other functor S? Is this also full? So what would that mean? That would mean that every just group homomorphism, we call them abstract group homomorphisms to emphasize that there's no geometric or algebraic or topological structure going on, just a group homomorphism between groups of points of algebraic groups. Is this the image of some map on algebraic groups between some affine algebraic groups? Okay. So this is
assuming that they're connected.
Probably, yeah. Most of what I deal with is going to be connected, I think. Yeah. Oh, you're talking about the Lie groups, you mean in Cartan's theorem? No.
No, I was talking about your question.
Oh, the algebraic groups. I think everything of relevance is connected. Yeah. Okay, so if the question here had the answer yes, okay, sorry, we'll get to that in a second. Just make a definition. This is just a definition saying we'll call an abstract homomorphism algebraic if it's the image of this quote unquote not really forgetful functor to the group of points. And so then the conjecture, which is sort of parallel to Cartan's theorem, so I'll call it Cartan's theorem for algebraic groups, would assert that basically every abstract homomorphism is algebraic. Right? But this is definitely false, and I'll talk about particular counterexamples in a second. Yeah, we'll do that next. So the first counterexample is very simple. It's just complex conjugation on the additive group over complex numbers. This is definitely not algebraic because we know what all the morphisms of algebraic groups from GA to itself are, right? It's spec of K box X. So you know what all the algebraic things look like, and complex conjugation is not one of those. We can generalize this a bit. We can just basically apply this on each matrix entry of a special linear group. So I'm using this hat to denote when I take some map of fields or algebras and I apply it to each entry of a matrix. So I'm calling conjugation hat the map from the special linear group over the complex numbers to itself. This is also not algebraic, right? Basically because the previous example is also not algebraic. And then let's not dwell too much on this counterexample, but this includes the previous one as a special case. You can take any two algebras, take an algebra homomorphism between them, and you can view these as groups of k points of some groups using Bay restriction, which I don't want to get into the details of. But this in general gives you something that's not algebraic. So this conjugation and the fact that they're algebra homomorphisms isn't necessarily the important part, but really the important part here is field homomorphisms tend to give rise to abstract homomorphisms which are not algebraic. So that's the main takeaway from our calendar example here. K-algebra maps, or more specifically, even just field maps, frequently sort of induce abstract homomorphisms on the groups of rational points, which are not algebraic. But roughly speaking, the philosophy of this area is that this is mostly the only obstruction. There aren't too many other obstructions. So what that means is that we sort of expect that if you just start with an abstract homomorphism rho here, you can generally factor it as a composition. And I think of sort of here, F hat is like the bad part. F hat is the part coming from a map of algebras or just a map of fields. And sigma is the good part, it's algebraic. Or if you're sort of, yeah, it's algebraic. So we expect this to be true, and I'll say why in a second, because of a result of Borel and Tits. But we call this sort of factorization a standard description. So the general philosophy is, under appropriate hypotheses, abstract homomorphisms should usually have standard descriptions. Any questions? Okay. So why do we expect this? The main result from Borel and Tits' original paper sort of initiating the study of this sort of thing is the following. So you have algebraic groups over some infinite fields, and then you have some hypotheses on your group. So G is absolutely almost simple, isotropic. G prime is absolutely simple and adjoint. And then if you look at an abstract homomorphism between the elementary subgroup of G into G prime, and if the image of the elementary subgroup is Zariski dense, then you do have this standard description as I described above. So you have this factorization into an algebraic part and a part coming, their version, it's actually, so it's an algebraic part and a part coming from a field embedding, not just a map of algebras, or not, yeah, specifically it's a field embedding. And then they also prove another version, which is a little more technical to state, so I haven't, but essentially you replace the assumptions on G prime with reductive. And I have another example here, which is a little complicated, which we'll talk about, which, well, we'll get into it, but essentially, so Borel and Tits show that if your image is reductive, then these factorizations, you only need field embeddings and algebraic things, basically. And this example will sort of motivate the transition to maps of algebras. So let's just take our special linear group over a field. So the linear algebra is, the Lie algebra is this trace zero matrices. And we'll take the ring of, the field of rational functions in one variable over a field K, and the derivative operator. So the important part of this derivative operator here is that it's a non-trivial derivation, It's a non-trivial little k derivation. And then we'll form this new group, which is a semi-direct product. So basically, this is a group G prime that sort of is coming with a Levy decomposition, because frac G here is the unipotent radical already, basically by construction. And you can define this map here. I don't want to get too much into it. Delta hat means, again, you put a hat over something, so you're sort of applying delta to each matrix entry. If this was, yeah, you are applying delta to each matrix entry. So this thing is not algebraic. I don't want to go into details behind that, but it does factor in the way sort of predicted by the conjecture, or by the theorem of Borel and Tits, even though this is, so the thing that's going on here is G prime is not reductive, right? G prime has unipotent radical, which is little g. So despite this, the situation does not satisfy the hypotheses of the Borel and Tits theorem, you get the results basically. And the way that you do that is you take your algebra of dual numbers. So this is dual numbers over your ring of field of rational functions. And you have this algebraic isomorphism between G prime of K and G of A, which is essentially coming from the definition of the Lie algebra. And this induces rho, essentially. So rho is the composition of this isomorphism sigma, which is algebraic, and F is is a map of algebras with Zariski dense image, and F induces a map F hat here on the algebraic groups, on the K points, I should say. So in this factorization, rho is, we have this good part sigma, which is algebraic, and a bad part F hat, which comes from a map of algebras. So the sort of what Borel and Tits do in their paper is they use this to motivate sort of the passage from just field embeddings, which is what you get from the previous theorem, to you sort of need to extend scope and look at maps of algebras. Let's keep going then. So here is the conjecture that they arrived at after proving their result, and then sort of looking through at this example, saying, okay, if you have non-reductive image, you need to not just look at field embeddings, but maps of algebras. So this is not exactly as they stated it, but sort of the version that is attackable. So you have a linear algebraic group and an abstract homomorphism out of it. You might as well embed your target into a general linear group. So we'll just replace G prime by a general linear group. And the hope is you can find an algebra A so that you factor rho here through G of A, and sigma, we're left with a good part sigma, which is algebraic, and sort of a bad part F hat, which comes from a map of algebras, which you do not expect to be algebraic. And the way that you think of sigma being algebraic involves something involving Bay restriction, but I don't want to say too much about that. Anyway, that's just how you view G of A as a group of points, rational points. Okay, so this is their conjecture. Let me say now a little bit about what's known. First, actually, we'll look at a super simple example here. This is how the conjecture, this factoring trick, sort of resolves the complex conjugation issue. So before we had this counterexample with complex conjugation, right? Complex conjugation gave rise to a map which was not algebraic. And this is rather sort of vacuous. All we're sort of doing is we're taking the map induced by conjugation, rho. We're saying it's not algebraic, but I can factor it as a composition of something coming from a map of algebras on the left and an algebraic thing on the right. Of course, in this here, the algebraic thing on the right is just basically an identity map. So it's not we're not doing anything fancy. We're just basically writing rho as the composition of the identity with itself. But that is exactly the sort of thing that this conjecture predicts should be done, should be able to do. Right? It can be done here. Right? So this previous counterexample is sort of resolved by this factoring notion. Okay, so what's known? Just around the same time as Borel and Tits did this result that I mentioned earlier and formulated the conjecture, Tits sketched the proof when the underlying fields are the real numbers. That's great. This 1973, this is the result I mentioned previously. They also had the G prime reductive version, which I haven't included here. There's a result of sites for perfect fields, or sorry, positive characteristic infinite perfect fields. Yeah, which I know not terribly much about other than what the result is. And then next up, we had some results of Lucy Lifshitz and Andrei Rapanchuk, which were the first sort of good results, general results in characteristic 0 for Chevalley groups. And then they have this sort of technical hypothesis about the unipotent radical of the image being commutative, which has sort of a spiritual successor in our new result as well. And then in 2011, Igor Rapanchuk, my advisor, proved basically the split case. So G is a split group, and then your target group is over algebraically closed field of characteristic 0. There's sort of more general statements here, but this is the main thrust of the result. He followed it up with some special linear groups over division algebras, which I'm not going to get too much into. And then our new result from this year is for a quasi-split group. So this special unitary group, SU2NLH. I'll talk about what that group is exactly. It's a quasi-split group. And the hope is that we can extend the methods for more general quasi-split groups eventually, but we haven't yet. And then we have this technical hypothesis, which is sort of descended from the hypothesis of Lifshitz and Rapanchuk on the commutativity of the unipotent radical of the image. It plays just a role in like one key lemma. But we sort of hope that we expect the result to be true without this hypothesis, but we haven't proved that yet. Okay. Well, let me state our new result a little more precisely. So let me describe this special unitary group. So we'll take a quadratic field extension in characteristic 0 and the Galois automorphism of it. So there's only one. Denote it by a bar, just like complex conjugation. And you can extend this to a tensor product by acting on L. And what we're going to do, so little h in, oh, I guess I think this big H in the title of the slide should be a little h. So SU2NL little h. The little h is a Hermitian form. It's skew Hermitian, but it's the same as Hermitian in this context. Of maximal Witt index. And this maximal Witt index assumption basically lets you write H as a block diagonal matrix like this. I mean, you can write H down as a matrix anyway, of course, but it takes this matrix form because of this assumption about the Witt index. And G is the isometry group of this Hermitian form. And you can write it as a matrix group here. So it's special linear determinant 1 matrices with this unitary condition here. X star HX equals H. X star is the conjugate transpose. And the entries are in a tensor L, not just A. Okay, so this is the group that we looked at. This is a special unitary group. And here's our result. So I'm switching from K prime to capital K for my algebraically closed field of characteristic 0. So you start with an abstract group homomorphism from the group of K points of this special unitary group into a general linear group. And then you have this technical assumption about the unipotent radical, the image. And the conclusion is that you have a standard description. So meaning you can find an algebra and a factorization through G over that algebra. And you have split rho into sort of a good part, sigma, which is algebraic, and a bad part, f hat, which comes from a map of algebras. Okay.
Okay.
Yeah.
I do not understand this condition. So that group, for example, rho g k bar.
Yeah.
Could it be, for example, purely unipotent? Or?
I'm not sure what you mean. So
no, because it's surprising for me how you can get a unipotent radical starting with a semi-simple group.
Oh, G is the special unitary group.
Yeah, yes. So it's semi-simple. Okay, you take the point, you take the image, you take the Zariski closure of that.
Yeah.
And then is there any example where this situation happens? I mean, when this unipotent radical is not commuted, is not zero? Is not trivial?
I mean, in general, rho can be very weird, right? Rho is just a group homomorphism. It's not, has no respect for the topological structures, right? So I feel like in general, it's very hard to say anything about rho of G of K. I don't know, maybe it's not. The whole point of this.
Okay. I believe you.
Yeah. Maybe you are something
else. Maybe to address your question. So like the example of Borel and Tits that Joshua described earlier, right? So there we're starting with SLN, but then we ended up with SLN over this string of dual numbers, which had a unipotent radical. So
yeah.
So this sort of thing might very well happen. So I mean, as Joshua said, we're looking just as abstract homomorphisms. So, you know, in principle, the image could have a unipotent radical. I mean, that's not something we can rule out automatically.
Okay, thank you. Thank you.
Mm-hmm. Question? Yes. Okay. So this is our result. And okay, let me sort of give a top-down view of the proof, and then we'll get into the details as there's time for it. So the first thing to do is construct this algebra A. So let me go back to this statement, this A here, the construction of it. It's the first place you start. You sort of get little f. It's sort of obvious what f should be once you've described A. And basically A is, so essentially A is going to be the Zariski closure of an image of a one-dimensional root subgroup under rho. And then another tricky thing you can do with A is you can endow it with the structure of an algebraic ring. I'll talk about algebraic rings a little bit, but you can make A into an algebraic ring. And that structure is sort of important for knowing more about A and what's going on. And then you want to define sigma, but of course, you don't have a presentation of G of A. So G of A is, well, G is a quasi-split group. And so you know that and A is a product of local rings, which all comes from the knowing that it's an algebraic ring. And that tells you something about a set of generators for G of A in terms of like a pinning. So the images of your unipotent, of your pinning maps generate G of A, but that you have nice relations like Chevalier commutator formula and so on. But those aren't all the relations. So you have to go to the Steinberg group where those are all the relations, and you can define your map out of that. And then the hope is in step 3, you can descend from the Steinberg group using tools from algebraic K-theory. So basically, we use some algebraic K-theory to measure sort of the difference between the Steinberg group and G tilde of A and G of A. And the kernel here is basically a generalization of algebraic K2. And there's an important result from Stavrova that this K2 analog here is central subgroup. So that's, you descend that to sigma, and then you have the map sigma that you wanted. So you know, obviously have to check that sigma is algebraic, but that's not actually the hardest part of all this once you sort of do all that. All right, let's talk about where you get A from. So I said, oh yeah, let's talk about this. So an algebraic ring, I've said A should be one. It's just an affine variety where you have a ring structure and the ring operations are regular. So this is maybe not super precise, but this is conceptually what an algebraic ring is. And we're going to make A into one. So how do we do that? Well, we don't have any A yet. So let me describe some pinning of this group. So it's not split, but it still has, you still do all the root system structure. So maybe this is all stuff people here know. You have root spaces. I'm going to denote the root space associated to a character alpha by V sub alpha. And we're looking at relative roots, so characters of some maximal split torus. Right? This is not a split group, so this maximal split torus is not maximal. And you get a root system of type Cn. So in general, with a non-split group, you could get a non-reduced root system, but this one is reduced. You get Cn. And the absolute type is An, or A, not the same N, but it's type A. And in the split case, right, all of your root spaces and root subgroups are dimension 1, but we have a quasi-split group, so you can get higher dimension for your root spaces. So in this group, you get some number that are dimension 1 and some that are dimension 2. And you can actually tell by the length of the root. You can tell that dimension. Yeah, and you can think of this, there's like a folding over of a type AN root system to get Cn, and well, anyway. So you have a pinning here, you have a root subgroup map, and these satisfy sort of the usual. So this is an embedding of schemes, but in sort of more generality, but because we have a reduced root system, this is actually an embedding of group schemes. That's what the first relation here says. The second thing is basically saying that X alpha maps into the associated root subgroup. So when you conjugate it by a torus element, you're acting inside by the character alpha of S. Then you have the Shuttle commutator formula, which is intimidating, but I won't say more about it. And then finally, I sort of alluded to this earlier, but G is quasi-split. It's this special unitary group. And so there's a lemma from Stavrova that maybe you can do this more simply, but there's a lemma that tells you that if you have a local ring, then basically this quasi-split group is its elementary subgroup over a local ring. And this is true for any quasi-split group. And because it's perspective products, you actually can do this for a product of local things. Okay. So this is what I was saying when I said G of A. So the A that we construct will be a product of local algebras. So G of A is, we have a generator set for it, and we know a lot of relations, but they're not all the relations because, well, we don't know they're all the relations at that rate. Okay. Okay, so this is all set up to define A. So we have our abstract homomorphism rho, and you given it a relative root. So this is a thing, it's like a character of some maximal split torus. You take the image of, so X alpha is really a map from V alpha into your group, but V alpha is usually one-dimensional. So if V alpha is one-dimensional, this A alpha is just the whole closure of the image of a root subgroup. But like I said, sometimes some of the root subgroups are dimension 2. And so in that case, what we're doing here is X alpha of K, you pick a one-dimensional subspace of your root space, and that's what X alpha of K is. So X alpha of K in that case is a one-dimensional subgroup of a two-dimensional root group. And then F is just the composition of rho with X alpha. Okay, so this A alpha here, right? X alpha of K, like I said, is a one-dimensional subgroup of G of K. Then we push it through rho, so we're in this general linear group. And we still have a group, but rho can do weird things, so we take the closure. And then what you can do is you can make A alpha an algebraic ring. And more specifically, in a way so that F alpha is a ring homomorphism. Well, the dense image part, that's just obvious from the definition. But so what does that sort of force on the ring structure of A alpha immediately? It immediately forces the addition in A alpha to be matrix multiplication, right? Because X alpha takes addition in K, addition in V alpha maybe, to matrix multiplication in G of K, and then rho preserves matrix multiplication. So the addition operation in this algebraic ring is actually matrix multiplication in this general linear group. And then multiplication, you have to define some multiplication which distributes over matrix multiplication. Right? So it has to look sort of weird and non-traditional. This goes back to a construction of Kasabov and Sapir. And then, so they were just doing this for some special linear groups. And then Igor extended this to split groups. And then one of the key parts of this new result is extending the construction for split groups to this quasi-split group, which is a little slightly complicated by the fact that you can have two-dimensional root groups, but it can be done. But it's just sort of computational, so I'm not going to go into this. And then another lemma is that essentially all these A alphas are the same. They're the same at least as varieties. And so we just think of having one of them, basically. So really what's going on is you pick some particular relative root, define the ring structure on A alpha for that relative root using this process, using this lemma, and then you just pass that ring structure to all the other ones using these variety isomorphisms. Okay. So this is where A comes from. And okay, let me say a little bit about algebraic rings sort of generally, because this, well, we now have an algebraic ring. This A is an algebraic ring. It's in characteristic 0, and it's connected. I guess I haven't really said why we know it's connected, but it's connected. And it turns out that basically determines the structure of A. So you can take any algebra over an algebraically closed field of characteristic 0 and just make it an algebraic ring. You just use Zariski topology as an affine space. It'll be an algebraic ring. And it turns out that this is essentially the only way to get algebraic rings in characteristic 0 over algebraically closed fields. So this is there's a whole section on algebraic rings in this original paper on split groups, and this comes from there. So this is, I guess, even a little more general. You have an algebraic ring in characteristic 0 over an algebraically closed field. It then has to be a sum of an algebra here and some finite ring. Right. So then if it's connected, then it just has to, you have to drop the finite part. Yeah, we know that this is connected for a different reason, another lemma. So this algebraic ring A that we've constructed is actually just a finite dimensional algebra. And okay, so it's a finite dimensional algebra, so it's a product of local things. And I said earlier that this lemma of Stavrova tells you, in that case, that this G of A, so this is the special unitary group with points in this algebra, you have a nice set of generators for it in terms of spinning. Okay. All right, back to the sort of top level overview of the proof. So we did this construction of A, and we endowed it with a structure of an algebraic ring. And now we need to talk a little bit about the Steinberg group next. And this is sort of where all the sigma starts. The map sigma starts. So we had these relations earlier. This is just commutator, Chevrolet commutator, and the fact that these are group homomorphisms for these generators of our group. So R here is an arbitrary algebra over little k. And so we just define the Steinberg group to be the same thing with the same with generators. We just put tildes over the generators and write down the same relations. And that defines a group as just an abstract group. And then you obviously sort of get for free this natural mapping from the Steinberg group to your group. And so the image is what we would usually call the elementary subgroup. But we know that if R is a product of local things, for example, this algebraic ring A that we've constructed, then it actually projects onto the whole group of A points of the group G. Okay. So that's what the Steinberg group is. This definition is due to Stavrova as well. She worked out some theory of generalizing Steinberg groups to reductive isotropic groups. You can define this sort of thing. Okay. Yeah, and then the main result, or one of her main results on this subject, is that the kernel of this canonical map is a central subgroup. So her notation here, this lines up with her notation a little bit more. P here is some fixed parabolic subgroup. So her construction of the Steinberg group and elementary subgroup in much more generality than I'm discussing requires fixing like a particular parabolic subgroup and everything sort of with respect to that. And then there's a lot of arguments that it doesn't depend on that too much, but anyway, essentially this kernel is central. So this, all the hypotheses here certainly apply to our special unitary group. So the kernel is central if it's over a local ring. And then we had to do a bit of a lemma just to work out that this thing respects products. So we just had to work out that the Steinberg group here respects products. But once you do that, you get immediately that this, for the special unitary group, this kernel, this sort of K2 thing is a central subgroup. So you just have to show that we're not obtaining any sort of new proof, it's just reusing the result. All right, so that's the algebraic K theory we need. All right, so this is all notation that we've already set up. So we have our special unitary group, we have our abstract homomorphism rho, we have these pinning maps X alpha, and an algebraic ring that we've constructed associated to rho, and you have this associated map to A. This is all stuff I've talked about. Here's a lemma we have to basically lift X alpha to A, sort of is what's going on here. Yeah, I'm not going to say too much about this. Essentially, what this is for is this is telling us what to expect sigma to map a generator X alpha V2. So we expect that sigma, right, when you want sigma to go from G of A to this general linear group, we expect it to take the generator X alpha V to psi alpha V coming from this lemma. And like I said before, you can't just define sigma to be the map which does this, because you can't show that that's well defined because you don't know all the generators for G of A, right? Or all the relations for G of A, excuse me. So you can define it on the Steinberg group though. So that's what you do. You send the tilde of one of these generators. So this is a generator of the abstract Steinberg group, and you send it to psi alpha. So this is what you expect it to do, at least you expect it to do on the bottom level, but all we can really define is what it does on the Steinberg group level. Okay, and then the hope is to descend this. Right? So we've now sort of defined the map on the Steinberg group, and we just want to get down to the group over this algebraic ring. And we'll make use of this fact about the central kernel here. This is all just repeating notation. I guess I have one bit of new notation here. I'm using capital H for the closure of the image of row. This is all, I guess I'm sneaking in one bit here, where's that sigma tilde maps into H. I guess maybe not sneaking in, maybe it's not terribly hard to check. And this is sort of a summary of what we're doing. So everything we've done fits into this diagram, basically. We have, so F is this map of algebras from K to A. It induces a map on the groups of points, which I'm calling F hat here, this vertical map. Sorry, not vertical, horizontal map. F hat also has a version on the Steinberg group. So you put a tilde over your hat. And you have these vertical canonical projections. We have rho that we started with originally, and we've constructed sigma tilde. And everything in the solid, everything involving solid arrows here gives you a commutative diagram. And all that's left is to descend sigma tilde down to a sigma. So it's dotted sigma. And then if we figure out this whole thing commutes, the bottom triangle here is the standard description that we wanted. We wanted to factor rho as a composition of an F hat and a sigma, and that's this bottom triangle here. So things get a little technical here. We can first, instead of descending all the way to sigma, we sort of go too far down. We can first map to H mod its center with something I'll call sigma bar. And you can do this. This is where you use the fact that this kernel is central, right? This is essentially a just first isomorphism theorem. So G of A is isomorphic to the Steinberg group mod this central kernel. We know sigma tilde is surjective by another lemma that I'm skipping. And this kernel is central, so it gets mapped into the center. And so just by first isomorphism standard sort of things, sigma tilde induces the sigma bar like you want. So this is where this algebraic K-theory stuff gets used. All right, so here's some more diagrams summarizing what we've got. So the left diagram I already showed you. The right diagram incorporates this new thing, sigma bar. We have H mod its center. Nu is just the quotient map from H to H mod its center. And sigma bar we constructed. And this sort of oblong rectangle on the right is the equation from the previous lemma. Let me scroll up. Sigma bar composed with pi sub A is nu composed with sigma tilde. That's this weird rectangle on the right here. Okay. And the next thing, so we still haven't showed any sort of algebraicity for anything, but you can show that sigma bar is algebraic. I'm not going to go into details because it's not that interesting, but essentially you can write G of A as the product of its roots groups and use some technical lemmas that are essentially algebraic geometry. Nothing super fancy. And sigma bar is algebraic. So this is where all the algebraic, this is where you really get the fact that sigma is algebraic from, because then you're just going to lift this to sigma. So that's what we'll do. We want to lift sigma bar up to sigma. So H again is the closure of the image, and we have this technical hypothesis that the unipotent radical of H is commutative. So I'm just repeating that. That's from the original statement. So essentially what we do to lift sigma bar up to sigma is you write down a nice Levy decomposition of G of A, and you lift sigma bar on each Levy factor, each factor of your semi-direct product. So this is the nice Levy decomposition I was just talking about. You can find, you can take the Jacobson radical of this algebra A and a really nice subalgebra, basically coming from the Wedderburn-Malseb theorem. So this A bar is a subalgebra. It's isomorphic to A mod its Jacobson radical. as an algebra, and A is also the sum of A bar with J. And it gives you this really nice decomposition. So GAJ here is a congruent subgroup. And that would be the kernel of some map from G of A to G of A mod J. And that's the unipotent part. And then G of A bar is the semi-simple part here, bar-Levy decomposition. And so where this star condition gets used here is in just one step in this. Using star, well, you show that the center of H is contained in the semi-simple part. So star sort of implies, roughly speaking, that star implies that that the center of H is contained in any Levy subgroup of G of H. Or sorry, this is a little imprecise. I guess I should say, instead of G of A bar, I should say the image of G of A bar under sigma or something. But yeah, this is where this star condition gets used, which lets you lift sigma bar on the unipotent part because I think brain is working slowly this morning. The center, well, yeah, let me not dwell on this too much. The unipotent radical of H is commutative, right, yeah. So sigma bar lifts on the unipotent part because of star, basically. And like on the unipotent part, it's sigma bar is just the same as sigma because nu is isomorphism. The other part is just some standard lemma from Borel linear algebraic groups to lift it on the semi-simple part. And so you've lifted it on both parts, and so you have this sigma. And it's algebraic because you lifted it from an algebraic thing. Okay. So at this point, we're basically done. We have this sigma. You just have to check that it actually makes this diagram on the left commute again. But these are sort of standard arguments. So you show, so the blue check marks here are things that we already know commutes. And then you can show that the upper right triangle commutes first by sort of, I don't know, a straightforward argument. And then it's an immediate consequence that the bottom triangle commutes from that because pi k is surjective. Okay. That is, I think, all I'm going to say about the proof here. I'll just restate this result. So you have this technical hypothesis on the unipotent radical, which we used at just one particular point in the argument. And yeah, we found a standard description of this abstract homomorphism rho. And that was what we set out to do. And in my last little bit, let me just say very briefly, so I said this earlier, but we hope that the same techniques can resolve this conjecture for quasi-split. So this is just one quasi-split group. It's already known for split groups, but the sort of key to extending it to this quasi-split group was just to be able to handle the two-dimensional root subgroups. Essentially, that was sort of the main issue to deal with. And so now that we've done that, hopefully we can look at more quasi-split groups. So for example, some special orthogonal groups I started looking at, and maybe other special unitary groups, sort of more general Hermitian forms instead of just this maximal bit index one. And that's the plan. And I think I have more time, but I will stop here.
Okay, thank you. Questions, comments? So you can use the chat, huh? Of course. Huh?
So this condition that the radical is commutative, is it possible, at least in theory, to weaken it?
Yes. So, for example, I have an argument written down that depends on, so one of the key steps was the centrality of this K2 thing, right? And in, say, the split case, we know that that K2 is generated by symbols, Steinberg symbols. If this K2 generalization is also generated by Steinberg symbols, then you can bypass the whole part of this argument where this technical hypothesis is necessary. So you can just, so I guess what I'm saying, we know the kernel is central. If that kernel is generated by Steinberg symbols, then an argument gets rid of this hypothesis. That helps. But I don't like, there's one thing I've looked at a lot. There's a thesis of Deodar, which proves generation of this kernel by symbols over fields for quasi-split groups. But we're not over a field. We're over like something that's very much slightly weaker than a field. It's a product of local rings. So I for a while worked on trying to generalize Deodar's results, but I couldn't quite figure it out. Hopefully that answers your question.
Yes, thank you.
Sorry, my microphone was mute. Other questions or comments?
So I have a question. Where do you use characteristic 0? Is this just in the Levy decomposition?
It's in, so the structure of A has some relationship to characteristic 0 of capital K here. Because of this, the structure of algebraic rings in characteristic 0 is more rigid than in positive characteristic. And then one other part of it is, so I should have said, well, in this, so in the results that resolve the split case, in the split case, there's results where you replace what I have called little k by a ring. And there you have some minor restrictions on characteristic of your ring based on which root system. So if you have type B or C or G, you need 2 to be invertible in your ring. And if you have type G, you need 3 to also be invertible.
Okay.
And that comes from this step where you construct the algebraic ring A. Defining the multiplication in A involves some division by 2 or 3 if you're in like type B and C. Sorry, it involves dividing by 2 if you're in type B or C. It involves dividing by 3 as well if you're in type G. And in our arguments as well, so this is type C. Yeah, you do have to divide by 2. So there's definitely some characteristic 2 obstruction coming from just from how you define multiplication in A. And also, yeah, anyway, another coefficient that shows up in denominators there is this, the square of your, so G is defined relative to some quadratic extension, right? So it's like generated by some non-trivial square root, basically. So the square of that shows up in denominators in some of the calculations as well. So that's another thing that probably rules out some, I don't know, it adds some assumption about the characteristic that you need.
Okay, thank you.
Okay. One other questions? Okay. So we thank the speaker again, and Erhard